Dear students, in last class you have learned how series resonance principle is used for obtaining AC high voltage required for testing purpose. Today we will have discussion on chief advantages of resonance principle. The first advantage is it gives an output of pure sine wave. It means that the high AC voltage obtained has got purely sinusoidal waveform. It is so because the core of the transformer will not get saturated. If the core of the transformer gets saturated, in that case, instead of getting purely sinusoidal AC voltage, we will be getting non-sinusoidal AC voltage as harmonics are produced. The second advantage is the power requirements are about 5 to 10% of total kVA required. Third advantage, no high current arcing and heavy current surges occur if the test object fails, as resonance ceases at the failure of the test object. In case the test object fails, here the test object fails, it means that the capacitor gets short circuited. Once the capacitor in the resonance circuit gets short circuited, then the inductance will become effective. That is, the impedance of the circuit will become R square plus XL square under root. In other words, we can say that the resonance ceases. Therefore, the current in the circuit reduces, and hence there will be no arcing and heavy current surges whenever the test object fails. Fourth advantage is cascading is also possible for very high voltages. If we need higher voltages, then we can go for connecting output of one transformer to another transformer and obtain the high voltages. The fifth advantage is it has simple and compact test arrangement, and the sixth advantage is no repeated flashover occurs in case of partial failures of the test object and insulation recovery. It means that if the test object fails and there is no insulation recovery, in that case repeated flashover will not occur as the resonance ceases. In addition to these advantages, there are two disadvantages of this method. They are the additional variable chokes capable of withstanding the full test voltage and the full test current are required. So if the additional chokes are required which can withstand the full test voltage and the full test current, the cost of the equipment will increase. Now we will solve one problem based on series resonance principle used in obtaining AC high voltages for test purpose. Problem reads like it. A 100 kVA 250 volt bar 200 kV feed transformer has resistance and reactance of 1% and 5% respectively. This transformer is used to test a cable at 400 kV at 50 Hz. The cable takes a charging current of 0.5 ampere at 400 kV. Determine the series inductance required. Assume 1% resistance of the inductor. Also determine input voltage to the transformer. Neglect dielectric loss of the cable. Solution. Given 100 kV 250 volt bar 200 kV feed transformer. Resistance and reactance of this feed transformer are given in percentage. R is given as 1% and reactance XL is given as 5%. We have to convert these into actual values. For that, we need the base impedance. Test voltage of the cable is 400 kV. Test current of the cable is 0.5 ampere. Frequency is given as 50 Hz. We have to assume resistance of the inductor as 1%. Resistance of inductor let me call it as R equal to 1%. First we will calculate base impedance of transformer, that is Z base equal to V square upon VA. That is equal to 200 into 10 raised to 3 whole square divided by 100 into 1000. On simplifying, we get 400 kilo ohm. Now using the percentage resistance and reactance of the transformer given to us and the calculated Z base, we will calculate actual resistance and the reactance of the transformer. Actual resistance of the feed transformer are equal to percentage resistance divided by 100 into base impedance. That is equal to 1 divided by 100 into 400. That is equal to kilo ohm. That is equal to 4 kilo ohm. Now similarly we can calculate reactance of the feed transformer. Similarly, write here actual reactance of feed transformer XL is equal to percentage reactance by 100 into Z base. XL equal to percentage reactance upon 100 into Z base. That is equal to 5 by 100 into 400 kilo ohm. On simplification we get 20 kilo ohm. Since the resistance of inductor is 1%, its value will be equal to R equal to 4 kilo ohm. The capacitive reactance of the test specimen XC is equal to voltage across test specimen divided by current through test specimen. That is equal to 400 kV divided by 0.5, which becomes equal to 800 kilo ohm. At resonance, reactance of feed transformer plus reactance of inductor will be equal to reactance of capacitor. The circuit used for the test actually appears like this. It is feed transformer primary, feed transformer secondary, resistance of inductor, and the transformer included here. This is additional inductor to be connected, and the test specimen, which is capacitive in nature. Current through test specimen is 0.5 ampere. Voltage across test specimen is 400 kV. We have to adjust XL such that we get resonance. Feed transformer may be shown with regulating transformer also by having an arrow mark over it. So in addition to this inductor shown here, we are having transformer inductance also. So reactance of feed transformer plus reactance of inductor is equal to reactance of capacitor at resonance. Using that, we can write reactance of inductor equal to reactance of the capacitor, that is 800 kilo ohm, minus the reactance of transformer, which is equal to 20 kilo ohm. So subtracting we get 780 kilo ohm. Given f equal to 50 hertz, therefore we can calculate omega as 2 pi f, approximately equal to 314 radians per second. Now inductance of additional inductor L is equal to 780 kilo ohm divided by omega, that is 780 into 1000 divided by 314, which becomes equal to 2484 Henry. Total resistance of the circuit is the resistance of transformer and the resistance of additional inductor, that is 4 kilo ohm plus 4 kilo ohm equal to 8 kilo ohm. Under resonance condition, transformer secondary voltage will be equal to voltage drop in this resistance, that is I into R equal to 0.5 into 8 equal to 4 kV. Now to get the input voltage, we have to transfer this secondary side voltage to the primary side of the feed transformer. So you can write, therefore input voltage is equal to secondary side voltage, that is 4 kV, into 250 by 200 kV, that is equal to 5 volts. Dear students, I will stop the class here and continue in next class with Tesla coil.